Hello viewers, welcome to the next section, Support Vector Machines. In this section we'll see how our support vector machine works in both linear and non-linear scenarios. We'll also learn to control the number of support vectors and use SVMs for regression problems. Now we move on to the first video of this section, Scikit-learn implementation. In this video we're going to take a look at linear classification, kernel-based classification, and some non-linear examples. In order to allow the model to have a more flexible separating hyperplane, all Scikit-learn implementations are based on a simple variant that includes so-called slack variables. The introduction of these slack variables allows us to create a flexible margin so that some vectors belonging to a class can also be found in the opposite part of the hyperspace and can be included in the model training. Let's perform linear classification. Our first example is based on a linear SVM. We start by importing makeClassification, numpy, and matplotlib. We then add this code for reproducibility. Here we have 500 samples. Then we create a dataset with this code. We've subdivided this dataset into two classes. This showXY code is used to show the dataset. Running gives us this plot. Notice that some points overlap the two main blobs. Scikit-learn also provides the Svc class, which is a very efficient implementation that can be used in most cases. We're going to use it together with cross-validation to validate performance. So add this code. Here we import Svc and cross-val score. The kernel parameter is set to linear in this example. Running this, we get the result as 0.9319. As expected, the accuracy is comparable to a logistic regression, as this model tries to find an optimal linear separator. Next, we're going to discuss how it works and how it can improve the SVM's performance dramatically in non-linear scenarios. When working with non-linear problems, it's useful to transform the original vectors by projecting them into a higher dimensional space where they can be linearly separated. Scikit-learn supports 3 different kernels that can solve many real-life problems. Let's look at them. First one is Radial basis function. The RBF kernel is the default value for Svc and is based on the function as shown here. The gamma parameter determines the amplitude of the function, which is not influenced by the direction but only by the distance. Next is the polynomial kernel, and it's based on the function. The exponent c is specified through the parameter's degree, while the constant term r is called cof0. This function can easily expand the dimensionality with a large number of support variables and overcome very non-linear problems. The sigmoid kernel is based on this function. The constant term r is specified through the parameter cof0. Normally, built-in kernels can efficiently solve most real-life problems. However, Scikit-learn allows us to create custom kernels as normal Python functions. Let's build a custom kernel. We import numpy, and then define custom kernel, and then add this line. The function can be passed to Svc through the kernel parameter. To show the power of kernel SVMs, we're going to solve 2 problems. The first one is simpler, but purely non-linear. So let's generate the dataset through makeCircle's built-in function. For that, we import this function. Then add this code for reproducibility. Then finally, we create the dataset and run it. When we run the showDataset command, we get the plot of dataset. As it's possible to see, a linear classifier can never separate the 2 sets, and every approximation will contain on average 50% misclassifications. A logistic regression example is shown here. As expected, the accuracy is below 50%, and no other optimizations can increase it dramatically. Let's consider a grid search with an SVM and different kernels, keeping the default values of each one. So, to perform this, we add this code. Here we've imported multiprocessing and grid search CV. Then we've defined paramGrid and created a train grid search on SVM classifiers with these 2 lines. Once we get the result, let's check the best estimator, and then check the best score. As expected from the geometry of our dataset, the best kernel is a radial basis function, which yields 88% accuracy. Further refinements on gamma could slightly increase this value, but as there is a partial overlap between the two subsets, it's very difficult to achieve an accuracy close to 100%. Another interesting example can be provided by the MNIST handwritten digit dataset. We've already seen it and classified it using linear models. Now we can try to find the best kernel with an SVM. This is the code to do it. Here we've defined a param grid and created a train grid search on SVM classifier. Once we get the output, we'll print the best estimator. Once we get the result, we'll print the best score. We get an accuracy of 98%. This means that a non-linear transformation with very hard margins can easily capture the dynamics of all digits. Indeed, SVMs have always shown excellent performance with this dataset, and their usage can easily be extended to similar problems. Another interesting example is based on the Olivetti face dataset, which is not part of Scikit-learn, but can be automatically downloaded and set up using a built-in function called fetch Olivetti faces. We import it and then add this code to download it. Through the data_home parameter, it's possible to specify in which local folder the dataset must be placed. There are 40 different people, and each of them is represented with 10 pictures of 64 by 64 pixels. The number of classes, 40, is not high, but considering the similarity of many photos, a good classifier should be able to capture some specific anatomical details. So let's perform a grid search with non-linear kernels. Then we create a train grid search on SVM classifier. Once we get this output, we add this line of code to get the estimator. So the best estimator is polynomial based, with degree as 2. And post that, we get the best score with this line. This confirms the ability of SVM to capture non-linear dynamics, even with simple kernels that can be computed in a very limited amount of time. It'd be interesting for the reader to try different parameter combinations or pre-process the data and apply principal component analysis to reduce its dimensionality. That's all for now, folks.